Welcome to our session on excitations and defects in quantum materials. Today, we are going to focus on what happens to a quantum material when we add a fluctuation and when we add also some localized fluctuation. And the basic idea is that if we have a quantum material with a very specific ground state, making fluctuations in this material allows us to understand what is the nature of the ground state. And in particular, today we are going to see that non-equilibrium responses in quantum materials can be computed with the equilibrium ground state, that the responses to fluctuations allow us to predict when we are going to have instabilities and when the ground state is going to change, and that we have emergent quasi-particles associated to these fluctuations. And finally, we will see that when we add localized impurities, we can learn what is the nature of the underlying quantum many-body state. So the plan for today is that we will first look at something that it's relatively classical, that comes from statistical physics, that is the response of classical magnets. Then we will move on to the quantum realm and see how linear response for quantum many-body systems can be systematically applied to compute fluctuations in quantum materials. And finally, we will see how impurity effects affect in a completely different way different states of matter. So the idea for today is that we are going to take a certain material. This can be a superconductor, it can be a metal, it can be an insulator, it can be a classical magnet, it can be a quantum magnet, and we are going to add some local perturbation in a point in space. And let us say that the point when we add the perturbation is the point at position x and time t. And then what we do is we measure what happens at a different point in space and a different point in time. And this measurement can be a measurement of the local magnetic moment. It can be a measurement of the local electronic density. It can be a measurement of the local density of the states or any other observable. And in general, we can characterize this type of experiment by something that we call a response function. That is essentially a quantity that tells us that we make a perturbation inside x, we measure inside x prime, and the perturbation is made at time t, and measured at time t prime. So if we know this whole response function, we essentially know what happens to the material when we add a perturbation anywhere at any time and we measure at any other point. And the idea is that we can use this formalism for any kind of fluctuation and any kind of measurement. So if you are adding fluctuations that are modifying the charge in one point in space and measuring the charge in some other point in space, this corresponds to the dielectric function. If what you do is to add a local magnetic fluctuation on one site in space and measure the magnetic fluctuation some other site in space, this is called a spin fluctuation. And if you make a change in the local temperature on one side and measure temperature on the other side, this corresponds to the thermal conductance. So this is something that we can effectively apply to any observable in a quantum material. And in general, there are, let's say, two main ways of experimentally measuring these types of responses. One way is just by adding actual perturbations to the material. And this case is, for example, the case when we have an impurity in a quantum material. So you can think about having a metal and then replacing one of the atoms of this metal for some other element. And when you make the replacement, you are essentially disturbing the ground state. And this is something that happens naturally in materials, thanks to impurities that appear during chemical synthesis. And in particular, when you replace one atom in a metal, you get something called Friedel oscillations that essentially allow you to see what the Fermi surface of the system is, and that we will address more in detail later on. And then another way of thinking about these types of perturbations is by thinking that you have an actual measurement, and the measurement itself essentially creates a fluctuation in the material. So you can think, for example, about a magnetic system, and that you, let's say, throw to your magnetic system, let's say, neutrons that have a certain magnetic moment, and this magnetic moment of the neutrons interact with the local magnetic moment in your magnetic material, and they perturb your system. And depending on how the interaction between the magnetic moment of the neutrons and the magnetic material is, you may have one cross-section or a different cross-section, and this essentially allows you to see what are the magnetic fluctuations in the magnetic material. This is how neutron scattering, for example, works. Even though these seem like two completely different strategies to see responses, the kind of information that we can extract from the system, it is very similar. And the formalism used for one can be very naturally applied to the other case. So in general, this response function that we mentioned before is going to depend on both the positions and the times. However, in most of the cases, we deal with systems that have some type of translational symmetry, like for example, a one-dimensional chain that has translational symmetry in the x direction, and that also the Hamiltonian is time independent, meaning that the only thing that matters is the difference between the positions in real space and the difference between the times. And if this is the case, then we can completely characterize this response function by its Fourier transform both in the spatial coordinate and the time coordinate. So in many cases, it is actually convenient to work in reciprocal space. So instead of working with the real space version of the response function, we essentially work with its Fourier transform. And this is what we are going to do in many cases today. So a typical experiment where we actually need this response function is actually something that we see already in classical electromagnetism, which is the case of the dielectric function. So you can ask yourself what happens if you add a perturbation in the electrostatic potential in one point in space, and then you measure how is the modification of the electrostatic potential in some other point in space. And the basic idea is that the relationship between the electrostatic potential that you add in one point and the one that you measure on some other point in space is proportional to what we call the dielectric function. And the idea is that this proportionality is linear. And this holds as long as your perturbations are small enough in comparison with all the other energy scales of the system, which is the case that we are going to focus on today. So to understand how this response of a system allows us to understand what's happening, let us focus first on a classical case, a case that comes directly from statistical physics, which is the case of a classical magnet, in particular a classical magnet at finite temperature. So if you think about a classical model for magnetism, like an Ising model for magnetism at finite temperature, what you actually have is at very low temperatures, the system orders, so all the spins align in the same direction. And then once you go above a certain critical temperature, then your system is disordered and you enter into a paramagnetic state. So one important question is whether if one can actually predict the existence of the ordered state when you are in the non-ordered state. So you can think that you have a material that stays at very high temperatures, well above this critical temperature for magnetic ordering, and you want to know if there's some specific measurement that it will be able to tell you that once you go at very low temperatures, then the system is going to order. And this, of course, a very relevant question, because if this actually works, it would allow us to know when a system is prone to give rise to another completely different state. We may not be able to know what is the nature of this state, but we will be able to predict what do we need to do in order to drive a system to a completely different state. So the basic idea is that for a magnetic system, one can actually answer this question in a relatively simple way. And the way to answer this question is just by looking at how the magnetization of the system depends on an applied magnetic field. So if you are in a paramagnetic phase, in the absence of a magnetic field, your total magnetization is zero. But once you apply a little bit of a magnetic field, then you are going to slightly polarize your system. And the proportionality constant between the magnetic field that you apply and the magnetization that you get is a quantity that comes by definition from linear response theory, and it's what we call the magnetic susceptibility, which by definition is the variation of the total magnetization with respect to the magnetic field. And now you can ask yourself, how does this quantity depend on temperature? So does it become bigger or does it become smaller when you take the system at higher or lower temperatures? And this is a question that one can actually answer using a classical statistical model, in particular by solving the Ising model using statistical mean field theory. And the basic idea is that if you have a paramagnetic system, namely a system that has no exchange coupling between the sides, then the magnetic susceptibility goes as 1 over T, so 1 over the temperature. So it becomes bigger at low temperatures, but it only diverges at T equal to 0. However, if you have a ferromagnet, then the dependence of the susceptibility as a function of temperature is 1 over T minus Tc, where T is your temperature and Tc is the temperature at which the material actually develops ferromagnetism. And this expression is actually valid in the regime where your system is paramagnetic. So actually, you have a different evolution in the paramagnetic regime when your system is prone to have ferromagnetic order than when your system is prone to have paramagnetic order. And finally, if you happen to have antiferromagnetism, meaning that your exchange constant is bigger than 0, then your magnetic susceptibility goes as 1 over T plus Tc. So there's a sign change between the ferromagnetic and the antiferromagnetic case. And this is actually easier to understand just by looking at how the different states are. So if you're in the paramagnetic regime, then the fluctuations are essentially dominated by temperature. And of course, the lower your temperature, the smaller the fluctuations, but you always have a finite susceptibility. In the ferromagnetic regime, you can think that once you are very, very close to the phase transition, then the system wants to become ferromagnetically very, very easily. And that is why you have a divergence in your susceptibility very close to Tc. And in the antiferromagnetic case, you can think that your system wants to polarize less than what it would like if it was a paramagnetic system. So this sign change here tells you that your fluctuations will try to counteract the effect of the external magnetic field. And one way of distinguishing this experimentally is just by actually plotting the measured magnetic susceptibility as a function of the temperature. So if you have a material that is paramagnetic, you will see something like this. So a curve that has a divergence at t equal to 0. If you have a system that is ferromagnetic, you will see something like this plot. So a curve that has a divergence at a specific critical temperature. And if you have an antiferromagnetic system, you will see that the curve has a divergence at apparently some negative temperature. So this procedure is a procedure that allows you to effectively know how your system is going to behave at very low temperatures just by looking at the behavior of the system at high temperatures. And this is the whole idea of perturbation theory. And this is the whole idea of trying to understand fluctuations in quantum systems in order to predict when exotic quantum states are going to appear. So for that, let us go a little bit into detail to linear response theorem. That is essentially the methodology that allows us to see how fluctuations in quantum materials behave. The basic idea is that for perturbation theory, we essentially need to consider two parts in our Hamiltonian. We consider one part that is what we call the unperturbed Hamiltonian. So in general, this is the Hamiltonian of the quantum system that we are interested in. This could be a magnet, this could be a superconductor, or a topological insulator, a metal, and so forth. And then we think that there's a perturbation in this Hamiltonian. And this perturbation is, for the purposes of today, a local perturbation, something like a local impurity or a local probe. And the question for us is whether we can actually infer the properties of the perturbed Hamiltonian using the unperturbed one. So, of course, we could try to solve the perturbed Hamiltonian for arbitrary perturbations, but that is, of course, something that is very, very challenging to do in general. So the key question is whether if there's some information in the unperturbed Hamiltonian that tells us how it's going to behave once we add a perturbation, so that by measuring the effect of perturbations, we can actually infer what is the information that the unperturbed Hamiltonian has. And the basic idea is that we can think that our total Hamiltonian is essentially the combination of these two terms. We have our pristine Hamiltonian, and then we have our perturbation. And if we assume that our perturbation is small, we can just add some small multiplicative factor over here. And now the idea is that every single observable, our Hamiltonian, including energies, expectation values of electronic density, expectation values of magnetization, are a function of this prefactor. We take L equal to lambda equal to 0, then we have the pristine Hamiltonian. If you have lambda equal to 1, then we have our full Hamiltonian with the perturbation. And in principle, we could try to think how we can get these explicit functions of lambda, including the ground state energy, any observable, such as the local magnetic moment or the electronic density, or even the wave functions. And the usual trick is that if we assume that this perturbation is small enough, we can actually do some Taylor expansion in the coupling lambda and obtain all these observables as a function of lambda. So for example, if we think about a specific observable, such as the electronic density or the magnetic moment, we can say that the full value as a function of lambda is the value in the absence of the perturbation, which is what we call the unperturbed value. And then there's lambda that comes from a Taylor expansion times some coefficient that essentially tells us how strong the value is going to change. And by definition, this coefficient is the derivative of the observable with respect to lambda, and this is what we call the response of our system. And by measuring this response, or by computing the response, we can effectively learn a lot from our ground state. So now the idea is that one of the first steps that we need to do in order to use this response theory and linear perturbation theory to understand our Hamiltonian is to expand our wave functions. And in general, if we think about a system that is described by free electrons, we could think that our wave functions of the system are essentially the wave functions in the absence of the perturbation times the perturbation, a set of coefficients, that is what we must determine, and then all the other wave functions that allows us to expand the rest of the Hilbert space. So the actual trick is to find these coefficients for each wave function in the system. And the idea is that one can just, let's say, make a Taylor expansion in a systematic way and show that the coefficients for an arbitrary perturbation V take this form in lowest order in V. And what is actually important here is to note that these coefficients are essentially proportional to matrix elements between one eigenfunction and another eigenfunction times the perturbation of the Hamiltonian, and then the energy difference between the two eigenfunctions. So perturbations can actually mix low energy states with high energy states, and this mixture is essentially proportional to 1 over the energy difference. And of course, this is valid as long as we do not have degeneracies in the Hamiltonian. And now the idea is that with these perturbed eigenfunctions, we can express any type of observable that we have in the presence of the perturbation. Of course, there's a very important question, which is whether if this expansion of the eigenstates for small lambda is valid. So we assume that a function has a Taylor expansion, but only analytic functions have a Taylor expansion, and they may have a certain radius of convergence. And of course, we are not guaranteed that this is applicable for all quantum systems. And indeed, it is not applicable in general. And they are several paradigmatic examples where perturbation theory breaks down even for arbitrarily small perturbations. And the most simple case is the case of an impurity in a metal that it's called the orthogonality catastrophe, that is essentially telling you that if you have an infinite number of sites and you put an impurity, then the overlap between the perturbed eigenfunctions and the original eigenfunctions is effectively 0. Another case that is very important is the case of the quantum spins in a metal that realizes the Kondo model. And in this model, we get some emergent energy scale, which is the Kondo temperature. And this Kondo temperature is non-perturbative with respect to the Kondo coupling between the local impurity and the electron gas. And another example is the case of superconductivity, where the superconducting gap actually is not perturbative in terms of the coupling constant that arises due to the attractive interaction. However, for us, we are going to focus today on cases where perturbation theory holds, so where we can actually compute the response and the fluctuations of our system using this linear response theory. And to focus on a concrete example, let us focus first on a single particle system. So we are going to take a metal, for example, that has a certain dispersion, for example, a quadratic dispersion, as shown here, and whose Hamiltonian is written simply in terms of the eigenvalues times the eigenstates. And if we have a metallic system, then essentially all the states below the Fermi energy are filled. So we have a many-body state that has occupation 1 for all these states, and then occupation 0 for all the other states. And the collection of points that have the highest energy is what we call the Fermi energy. And this is going to be very, very important afterwards, because once we add a small perturbation, then essentially all the states that get rearranged are mostly the states that are at the Fermi energy. So to start with, it is useful to think first about how we write down the ground state of a Hamiltonian like the previous one. So we have our Hamiltonian that has the eigenenergies, has the eigenstates, and of course the different field operators fulfill the typical fermionic anti-commutation relations. And the idea is the many-body ground state is the state where we fill all the sites or all the levels that are below energy 0, and all the levels above energy 0 remain unfilled. And essentially this is done because a state built in this way is the state that minimizes the energy, because it's the most negative state that we can ever build. And the energy of that ground state is essentially the sum of all the single particle energies, which is the most negative number that we could build using the single particle energy that we have in our original Hamiltonian. And this is going to be important because this filling that we have in the ground state is going to determine the expectation values of several field operators. So our ground state is essentially a state where all the states that have energy smaller than 0 are filled. So these are all the creation operators for those states. And then by definition, the expectation value of psi dagger alpha psi alpha is going to be 1 for occupied states, and it's going to be 0 for unoccupied states. So this comes directly from the definition of the ground state. And again, as before, the ground state energy is the sum of all the single particle eigenvalues with energy smaller than 0. Now we are going to take this ground state and we are going to apply perturbation theory. And the idea is that we are going to take as unperturbed Hamiltonian or Hamiltonian with kinetic energy that has the ground state wave function that we described before, and our perturbation is going to be just a local on-site energy. So we are going to change the electrostatic potential of a single site. And the idea is that we want to know what happens when we take an electronic system that is actually a metal, and we change a little bit the chemical potential in one site in order to see what happens in all the other sites. So we want to see how the charge in the whole system rearranges once we make this small perturbation. So the quantity that we are interested in is the electronic density in site n after the perturbation minus the electronic density in site n before the perturbation. And this is essentially what we call our response theory. And the idea is that this response, if our system has rotational symmetry, is essentially going to depend only on the distance between site number 0 and site number n. So we can effectively do a Fourier transform, and this response function in reciprocal space is essentially the object that is going to be most important for us. Now, the basic idea is that if you just take the definition of your wave functions using perturbation theory, you plug them into the formula for the, let's say, density of your system, you will automatically get the following formula. So you can recognize this 1 over epsilon k minus epsilon k plus q. This comes directly from perturbation theory. And then this nk and a k plus q is actually the occupation number. So 0 and 1. And the basic idea is that this response function is going to be non-zero only when we have a state with momentum k that it's occupied and a state with momentum k plus q that it's unoccupied. If the two states are occupied or the two states are unoccupied, then this quantity is 0. So all the contributions come from states very close to the Fermi energy, right above it, or right below it. And that is why the Fermi surface is going to be very important from now on. So something very important to note is that if you have, for example, a one-dimensional bond structure, and you start asking yourself, well, where are the most important contributions to this term coming from, you very easily realize that the contributions that are most important are those that make this term here equal to 0. So occupied states with energy epsilon and empty states with energy epsilon, meaning that an occupied state, for example, at this k point, and an empty state at this k point are going to give rise to a very large contribution to the response function. And in particular, the response function is going to diverge when you have two states, one that it's occupied, one that it's empty, with nearly the same energy. What this actually means is that if you have a perturbation that has this very same Q vector, then this is going to create a huge response in the system. Because remember, this chi of Q tells you how strong the response of the system is going to be once you make a perturbation with wave vector Q. And this is something that one can compute in a more systematic way if you also ask yourself what happens if I make this perturbation time dependent. So if you actually do a time dependent extension of the previous procedure, you will get automatically that the response function is now going to take a very similar form as before, but now that you're going to have a frequency here in the denominator. And the basic idea is that if you take omega equal to 0, you recover the previous form. And if you take a finite omega, you are essentially asking you what happens if I make a perturbation with frequency omega and wave vector q. And in particular, if you take a one-dimensional electronic structure like our one-dimensional chain and compute this response function that now is frequency and momentum dependent, you will obtain the following plot. What this actually means is that you have a whole collection of omega versus q where there are, let's say, divergences and very strong contributions. And this is something that comes directly from the electronic structure. If you change your dispersion of the one-dimensional chain, then the shape of this charge, dynamical charge response, is going to change completely. So the dispersion alone is going to determine what the response of the system is going to be to fluctuations. And this is something that applies not only to one-dimensional systems, but also to two-dimensional systems. So if you take a two-dimensional system like a squirrel array that has a typical dispersion like 2 cosine of kx plus 2 cosine of ky, what you get is that at very low chemical potentials, like this one, you essentially get a circle for your Fermi surface, and then when you compute your charge response function, in particular the imaginary part, that it's the one that tells you about the divergences, then you get a circle like this one. What this actually means is that for q vectors inside this circle, when you add a perturbation with that q vector, you will get a sizable response. And if you have a q vector that's very far from the circle, then the response of the system is going to be relatively small. This is actually telling you that the response of the system is directly coming from the Fermi surface. So by measuring responses of a system due to small fluctuations, you can actually infer what the Fermi surface is. And this is actually the whole idea behind quasi-particle interference. In that case, what we actually do is we take a two-dimensional metal and we add impurities, and we look at how the electronic density is modulated by the impurity. The impurities act as some small perturbation, and so by looking at the wavelength of those impurities, we can infer the Fermi surface. There's also something very important about this response function that is associated to very specific Fermi surfaces that have something that is called nesting. And a way of thinking about this is the following. So let's imagine that you have a square lattice that has a square Brillouin zone, and let's imagine that our Fermi surface takes this form. So we have essentially lines. Instead of having a circle, we have a square. And this actually happens if you have a square lattice with first neighbor hopping, and you look at the Fermi surface at half filling. Now, the idea is that for this Fermi surface, you have many states that are almost empty or almost full that are connected by the same k vector, and in particular, this q vector over here. So the idea is that if you take q equal to 1 plus minus 1, then you will have a huge amount of single particle states that will make this term in the denominator 0. And so you are going to have a massive divergence of this response function. What this actually means is that your system is going to be extremely prone to instabilities with this q vector. If you have some small fluctuation with this q vector, then your system will likely completely reorganize because the response is infinite. And of course, quantum systems cannot have a response that is infinite in magnitude. So when you get infinite, what actually means is that your system is unstable. And this is actually the major trick of perturbation theory and of looking at fluctuations in quantum systems. If you have a system that you see is going to have a divergence when you add a small perturbation, then what that actually means is that there's a new state of matter that will appear once you add the perturbation. So a strategy that is very useful to predict new states of matter is by looking at the conditions for a system to be unstable, and in particular, by looking at the fluctuations that will make your system diverge. Or in other words, the fluctuations that will completely break down your ground state. And a very successful idea of this is deals with the case of interacting systems. So you can think now that a perturbation to your system doesn't have to be some, let's say, local impurity or local magnetic moment. Interactions themselves could be a perturbation. And the basic idea is that you could consider that you have a system that it's non-interacting, that has a certain response chi0, and then what you want to do is you want to compute what is the response of the system in the presence of the interactions, and this response is chi. And the idea is that the divergences of chi and chi0 may be different. So you need to answer two questions. First question, well, how can I find the response of my interacting system as a function of my non-interacting response? And second, once I have the response of my interacting system, how can I see when am I going to have fluctuations that are going to completely break down the ground state? And so let us answer for the first question, how we can compute the response of a system with interactions as a function of the response of a system without interactions. And the idea behind this comes from just perturbation theory. And this is something that can be systematically done using Feynman diagrammatics. But let us just look at a very simple example over here. So you can think that, for example, for the charge response, the response of your system is a diagram that looks like this. So you have density over here, then there are a bunch of interaction between electrons and density over there. If you now think that you have interactions between electrons, then you can expand this whole interacting response function on the non-interacting response function plus the non-interacting response function times an interaction between electrons times the non-interacting response function and so forth. So you will have the non-interacting response function once, twice, 3 times, and so forth. You can take a common factor with the non-interacting response function, and then you will get the same, let's say, object that you want to compute, which algebraically you essentially write in this way. So the basic idea is that the interacting response function can be expanded as a power series of the non-interacting response function. And then this power series can be summed, of course. And this is just the conventional summation. And when you do that, you actually end up with this formula. This is what is called the random phase approximation. And this is, in a way, let's say a perturbative formula, but non-perturbative at the same time. So you are, of course, doing perturbations on the electronic interaction. So the powers that we were summing were interaction to the power of 1, interaction to the power 2, interaction to the power 3, and so forth. But of course, you are summing also an infinite number of them. This type of approximation does not hold for every interacting system, but it holds in many cases for metals, actually, and it's going to be extremely useful to predict a new quasi-particle in a metallic system called a plasmon. Now, the basic idea is that this interacting response function can have two different types of divergences. And the divergences may come, on one hand, from the original non-interacting response function, which is what we called chi0, or they may come from the whole new mathematical structure of the system. So the basic idea is that if you have a divergence in the response function, then this divergence in the response function, it is usually associated to some excitation in the system. And the simplest case to understand is the case of the non-interacting response function. In the case of the non-interacting response function, we saw that the divergences were coming when we were having a state that was empty and a state that it was occupied. And that is what we called an electron hole excitation. We take a level that it's filled and we move that electron to a level that it's unfilled. And in non-interacting systems, those are essentially the excitations that give rise to the charge reorganization when we add an impurity. But if we have a interaction in the system, and in particular a long-range interaction like the Coulomb interaction, then there could be divergences that are not associated to the single particle energies, divergences that essentially come from the Q dependence of the interaction. And these are what are called plasma excitations, and in other words, plasmons, a new type of quasi-particle. And the dispersion relation of these plasmons actually depends strongly on the screening of the system. It also depends strongly on the dimensionality of the system. But just to make things concrete, in certain cases, it can have just a Q square dispersion. So it is like a conventional dispersion relation, Q square, but with the difference that it comes from electron-electron interactions. And from a physical point of view, it corresponds to a collective motion of the charge of the system, a collective motion that is facilitated by the long-range electron-electron repulsion in the system. And something that is also very important from these fluctuations is that we can try to see when the interacting response actually diverges, not in the case of charge excitations, but in the case of spin excitations. So if you start, for example, with a Hubbard model, you can actually think that this Hubbard interaction is very similar to the interaction that we proposed above. It is actually a charge-charge interaction, and one can do an RPA summation and ask oneself when is the full response function going to diverge. And what one actually finds is that the divergence of the response function happens when u times the non-interacting response function is 1, and the non-interacting response function is proportional to the density of states. So a Hubbard model actually becomes unstable once the density of states times the interaction is 1, which is what creates a divergence here, which is, of course, the standard criteria for magnetism. So in other words, this summation of the response function actually allows you to know when magnetism is going to appear, just because your electronic system is unstable to those perturbations. And in particular, it's something that can be systematically used to predict both magnetism, charge density waves, and even superconductivity. In each case, one needs to compute a different response function, and one needs to include interactions in a different way. But in all these cases, one can actually find that there's going to be an instability driven by some very specific type of fluctuation. In some cases, it's going to be repulsive, and in some cases, it's going to be attractive. Okay, so that is everything that I wanted to tell you about fluctuations in quantum materials. And now let us focus on a very specific type of fluctuation that is perhaps the most physical one, which is the case of impurities in quantum materials. So the basic idea is that if you have a system that it's pristine, that it's uniform, you can actually learn a lot about the system just by adding a local perturbation, like an impurity, an actual physical impurity, and seeing how the system rearranges itself. And in the following, let us comment on 4 different examples of this. So we are going to look at what happens when you put an impurity in a metal that we already anticipated before. What we are going to put impurity in a topological insulator. What happens when we put impurities in superconductors? And finally, what happens when we put impurities in quantum magnets? So let us start with impurities in metals. And this is, of course, building up on the idea that we presented before. The idea is that you can start with the Hamiltonian of the metal and then add a perturbation that is effectively an on-site energy. So you can think that an impurity is just a local modification of your on-site energy. But when you add this sort of impurity, you are actually breaking the translational symmetry of the system. So your system is no longer translational symmetric, but it has some, let's say, local perturbation in one side in space. And in particular, when you put this impurity, you are going to essentially mix the different eigenstates of your Hamiltonian. But this is, of course, something that you can do systematically using perturbation theory. So perturbation theory does not assume that you have translational symmetry. You can just use it with any eigenstates and any perturbation. And in particular, if you directly apply the formula for perturbation theory to compute the local density of states, which is essentially the change in the charge density as a function of the local chemical potential, what you actually observe is that the change in the local density of states is essentially proportional to matrix elements between your states in the Fermi surface, K and Q. And if you have a parabolic band, this essentially gives rise to a change that looks like cosine of kfx, and of course with some decay in space. So in short, when you add an impurity in a quantum material, you actually have fluctuations of the local charge density or the local density of states that essentially reflect the Fermi velocity of your system. And it's something that one can, let's say, systematically compute. So let us take, for example, a one-dimensional model. So this is a one-dimensional chain that is represented by a first neighbor type banding model, and then we add a local perturbation inside 0. If you put the chemical potential almost at the very bottom of the band and look at how the local density of state changes around the impurity, what you observe is the plot on the left. The local impurity is at site number 0, and the density of states is essentially oscillating in space and eventually converging to some very specific value. And this wavelength of the oscillation is essentially 2 times the Fermi wavelength of your one-dimensional model. And this is something that you can systematically see just by changing the chemical potential, which effectively increases your Fermi wavelength, and essentially that is going to make oscillations much faster in space. And when you do that, you essentially see this plot over here. So you still have oscillations, but now the oscillations are much faster. And of course, this is going to converge to a very specific value once you go far enough from the impurity. And of course, this also works in 2 dimensions. So if you take one impurity in a 2-dimensional system like a square lattice, what you actually see is that if the impurity is in the middle, then you have this sort of modulation in space of the local density of states. And you see that some wavelength emerges in the system. And of course, once you increase your chemical potential, then you still see the modulations in space, but now they are much faster. And this is effectively what one would measure using scanning tunneling microscopy. You actually measure the local density of states in real space. So by mapping in it around impurities, you can effectively extract what is the Fermi velocity of your system, and the Fermi wavelength, of course. Let us now move on to superconductors. And superconductors are actually very special in a sense that they are technically electronic insulators. Single particles, single electrons need to pay a finite amount of energy in order to enter a superconductor. So we are not going to have oscillations of the local density of a state as we have in metals, but we can still have a very non-trivial effect coming from impurities. And then very non-trivial effect essentially comes from adding magnetic impurities. So instead of adding a, let's say, non-magnetic moment, we add a magnetic moment in one side in space. So what we are going to assume is that our Hamiltonian is now the Hamiltonian of a superconductor plus some local exchange perturbation. So this is effectively a magnetization in the z direction in one very specific site in space. And to qualitatively understand what's going to happen here, you can just think about how the ground state of a superconductor looks like. In a superconductor, we essentially have a ground state that is formed by Cooper pairs. And you can think that Cooper pairs in conventional S-wave superconductors, they are effectively made of one electron up and one electron down, and they form a bound state. Forming a bound state actually means that in order to break this state, you need to pay a finite amount of energy. Now, when you add a magnetic impurity, if this magnetic impurity is coupled antiferromagnetically to your superconductor, then essentially it is helping you break a Cooper pair. And you can actually think that when you add a magnetic impurity, you are essentially lowering the energy barrier to break one very specific Cooper pair. So magnetic impurities in superconductors are going to create in-gap states in the superconductor because they help you break one of the Cooper pairs. And to understand the difference between a magnetic impurity and a non-magnetic impurity, it is very important to note one very specific point, which is that non-magnetic impurities do not break time reversal symmetry, and Cooper pairs are actually robust to perturbations that do not break time reversal symmetries, just because they do not change the energy between up and down electrons. So they do not help you break, let's say, one of the Cooper pairs in a sense that both the spin up and the spin down have exactly the same energy, whereas a magnetic impurity distinguishes between spin up and spin down, which in terms of symmetry means that it breaks time reversal symmetry. This is going to have very important consequences. So for example, if you look at the density of states of a superconductor, a conventional S-wave singlet superconductor without a non-magnetic impurity and with a non-magnetic impurity, you essentially see the same. So you see a superconducting gap, and this superconducting gap, of course, depends on the attractive interactions, but the spectra is roughly the same in the presence or absence of a non-magnetic impurity. This essentially comes from the fact that non-magnetic impurities do not help you break Cooper pairs in conventional superconductors. But if you now look at what happens when you add a magnetic impurity, what you actually see is that in the presence of a magnetic impurity, there's an in-gap state in your superconductor. What this actually means is that you can actually create an excitation in the superconductor by paying an energy that is smaller than the superconducting gap. And of course, if you don't have a magnetic impurity, then such gap does not exist. You can do this systematically as a function of the exchange coupling that you have between the magnetic moment and the superconductor. And that exchange coupling is what we call J here. And what you actually see is that for 0J, of course, there's no bound state because this would be a pristine superconductor. As you increase the value of J, then an in-gap state appears that at some point actually states at zero energy. So at this point, you can actually insert an electron in your superconductor for free. And then afterwards, if you keep increasing it, then the state goes to finite energy. And this point here actually marks a phase transition. This is a phase transition between a superconductor where all the electrons are paired to a superconductor where exactly one Cooper pair is broken and you have one dangling spin 1/2 in your system. So the many-body state of this system is spin equal to 0 in terms of the ground state of the superconductor, and here is spin equal to 1/2. Okay, let us move on now to a different type of impurity, which is an impurity in a topological system. And the specific impurity that we are going to focus on is a vacancy, which is the strongest type of impurity. You can think that a vacancy is like completely removing one side from your material. And this is convenient for topological states because in topological states, we always have, let's say, bounded states if you have a hole in the system or at the boundaries of the system. So you can actually think that a vacancy is the most extreme case of a hole in a system. It's essentially a hole in the topological insulator that became smaller and smaller and smaller until it had the size of a single side or the size of a single atom. But of course, you can think that if you have topological bounded states, when you have a big hole in your topological insulator, then those bounded states may survive as you make the hole smaller and smaller and smaller to the limit where you have a vacancy. So in other words, topological systems are very prone to have in-gap modes when you put local vacancies. And this is something that one can explore systematically. So you can take, for example, a topological superconductor. This is a spin triplet chiral superconductor. And you can see that if you don't have any impurities, you have a superconductor that has a full gap. You cannot know at all that this is a topological superconductor from it. But then once you add a local vacancy, that is essentially analogous to put an infinite on-site energy in one of the sites, then you see that an in-gap state appears. And let me emphasize that this is effectively a non-magnetic impurity. You can think that this term completely doesn't break transversal symmetry, it completely respects it, and even in the limit when V is infinite. So in a topological superconductor, you actually get bounded states even with non-magnetic impurities and in the extreme case of a vacancy. So if you have a superconductor and you see that in-gap modes appear when you have vacancies, then that is a signature of topological superconductivity. You can actually also explore this idea in the case of topological churn insulators, so systems that have a finite churn number. And for example, if you take a system that has a finite churn number and then you add also a local impurity and you take the value of that impurity to infinite, you are going to create a vacancy. And when you add the vacancy, you essentially create an in-gap mode in your churn insulator. If you had a conventional insulator, then you wouldn't have this in-gap mode. So this is also another way of identifying when you have a churn insulator. If you put vacancies and in-gap modes appear, then it is very likely that your system is topological. And then the last case that we are going to discuss is the case of quantum magnets. And quantum magnets were essentially the states that appeared when you had a Heisenberg model that was frustrated. So it was dominated by quantum fluctuations. And these quantum fluctuations essentially gave rise to a grounded state that didn't break transversal symmetry and that effectively had spin equal to 0 in every single site. So once you have this system that is completely non-magnetic, you can ask yourself what would happen if you make a very, very small magnetic perturbation close to your quantum magnet. Eventually, very far from the magnetic impurity, the system is going to be non-magnetic, but if you are close enough, there may be some magnetization induced by this impurity that you are adding. And one way of understanding what's going to happen, at least in the simplest case of spin 1/2, is by starting with a simple model for a quantum magnet, that in this case is a spin 1/2 Heisenberg model, and using a replacement of spin operators by spin-on operators, by auxiliary fermions. So the Hamiltonian that we are going to focus on is this one. We have first neighbor Heisenberg coupling. This gives rise to a quantum disordered state. And then we have a local magnetic impurity that effectively creates a local magnetic moment. And we are going to transform this whole Hamiltonian into a fermionic Hamiltonian by doing this auxiliary fermion replacement, in which every single spin site is replaced by a rigorous of fermions that we can consider that are spinons, the fundamental excitations of a quantum spin liquid. And of course, in order to keep the let's say, dimensionality of the local Hilbert space, we must enforce this constraint on the fermions. We make the replacement of the Heisenberg model, then we do a mean field decoupling of these new auxiliary fermions, and what we obtain is effectively a tie-binding Hamiltonian for the spinons in the quantum disordered system. And if you look at this Hamiltonian, you very easily realize that the Hamiltonian essentially looks like the Hamiltonian of an impurity in a one-dimensional electronic model. So actually the screening of magnetic impurities in quantum magnets, it is actually very similar to the screening of a local electrostatic impurity in a one-dimensional electron gas. Of course, the mapping that we did before is only valid if you have a spin 1/2 quantum disordered magnet, which is the case in which we can use this replacement of mapping the Heisenberg model to a spinon model. But there are quantum magnets that have higher quantum spins, and in particular spin 1 Heisenberg magnet. So the question is whether if there's a fundamental difference between these two cases. And the answer is actually yes. So if you think, for example, about the one-dimensional Heisenberg model, and you consider two cases that have quantum magnetism, spin 1/2 and spin 1, you actually get a completely different response in your system. So the ground state in both cases, in the absence of an impurity, is actually a spin liquid phase. So you have spin equal to 0 everywhere and a ground state that it's entangled. But if you have spin equal to 1/2, then the expectation value of the magnetization as you go away from the impurity that it's inside number 0 starts oscillating because of the antiferromagnetic interaction, and it decays in space, but it decays relatively slowly, and actually decays as a power law, like 1/n. Whereas if you focus on the spin 1 model, you also see that the magnetization is oscillating in space, again, due to the antiferromagnetic interaction, but the decay is actually much, much faster. And the decay is actually exponential in the case of spin equal to 1. And there's a fundamental reason why this happens. Spin 1/2 models are actually gapless. In particular, the uniform spin 1/2 Heisenberg model. And they are gapless because the tie-binding model for spinons is also gapless. It realizes a one-dimensional tie-binding chain. However, the spin 1 Heisenberg model in a linear chain has a gap. One needs to pay a finite amount of energy in order to go from the ground state to the excited state. And this finite amount of energy essentially induces a correlation length in the material. What this actually means is that spin information cannot propagate forever, and it decays very quickly exponentially, very much like charges in an insulator. So this system is actually a gapped quantum magnet, whereas this other system is a gapless quantum magnet. And by looking at how the response of a system to an impurity decays in space, you can actually know if your system is gapless or is gapped. If the response of your system decays as a power law, then your system is gapless. This means that information can propagate very far, being charge information or spin information. If your correlations decay exponentially, then you know that your system has a gap, and the size of the gap actually depends on the prefactor that you have in the exponential, in the correlation length. Okay, so finally, let us move on to a very specific case or a very specific phenomena that is actually driven by local impurities, which is the case of Anderson insulator, and is the case of Anderson localization. So far, we have been thinking just about individual local impurities, but in many cases, instead of having just one impurity, you have many at the same time. And if you have a single impurity in a quantum material, you may think that your ground state is not going to be affected, at least not the ground state of the whole material. But once you have many, many impurities, perhaps your ground state is going to be completely different from the original state. So one of the important consequences that impurities, in particular when they are put in a random way, they break translational symmetry. So now the case that we are going to focus on is what happens if translational symmetry is broken. And in particular, there are sort of three different regimes for translational symmetry. There's, of course, the regime where translational symmetry is conserved, which is the case that we have been considering so far. And if you have, for example, a system that has n sides, with n a very large number, actually the weight on every side is something like 1 over n. What this means is that you have essentially wave functions that live in all the sides with roughly the same weight. There's actually one case that it's in between a disordered system and a periodic system, which is the case of quasi-periodic systems. These are systems that they are not periodic in space, so you cannot choose a unit cell that repeats itself in space, but the way in which they change in space is actually not random. It's very predictable, and it follows, let's say, very specific rules. These cases are actually extremely interesting because they usually give rise to wave functions that are not plane waves, but that they are localized according to a power law. So they are not normalizable, because a power law is not normalizable, but they actually are localized more in some regions in space. And this is what are called critical wave functions. And then if you have a system that has disorder and very strong disorder, like many very strong local impurities, then what happens is that most of your electronic states are going to be localized around your impurities. And in particular, most of your wave functions are going to have some specific localization length, and they are going to be normalizable. Let us first look at the case where we have quasi-periodicity, where we have a perturbation that it is not periodic in space, but that it's also not random. And a simple way of writing this perturbation is just by taking a one-dimensional time-bending model and adding a local on-site energy that changes from site to site with a cosine-like modulation. And the modulation of the on-site energy is given by a certain wave vector that here we call Q. And the deal is that if this Q is an irrational number times 2 pi, then this potential is never going to repeat itself, so the system does not have any translational symmetry. If you look at the eigenstates of this Hamiltonian as a function of the strength of the potential, you actually find something quite interesting. And the way to understand them is by computing something that is called the inverse participation ratio. This essentially consists on taking your wave function, let's say, putting it to the fourth power and summing over all the sides. And the idea is that the inverse participation ratio takes completely different values depending on whether your wave functions are extended or if they are localized. If they are extended, psi of r goes as 1 over n, so the IPR essentially decreases as your system becomes bigger and bigger and bigger. If you have critical states, then your wave functions are going to be follow a power law behavior. And if you have localized states, then your wave functions are going to be localized around some sites in space, and then the IPR is going to be relatively large. What you actually see is that for this quasi-periodic model, we essentially have a transition between states being delocalized in space and then states being localized in space. So we can actually have a system that breaks translational symmetry, and yet their eigenstates are completely delocalized. So for example, our potential strength 1, your system is not translationally symmetric, your system is not periodic, but actually the eigenstates are still plane waves. They are still living in the whole system. Once you make your quasi-periodicity strong enough, then the states are localized and they live in a few sites in space. Of course, this type of localization also may appear when you have pure disorder. And in general, you can think that a typical Hamiltonian for a disorder system is going to have some, let's say, periodic hopping, that this can be in a one-dimensional system, two-dimensional system, and so forth, and then some random potential. And this random potential can be parameterized as some strength that here we call W, and then some set of random numbers that go between -1 and 1. And now the question is, well, what happens to the properties of this Hamiltonian, in particular the eigenstates of this Hamiltonian, as you increase the value of W? So what it's clear is that if you have W equal to 0, then you have a metal. So the system essentially has the electronic structure given by the periodic Hamiltonian. And then if W is infinite or very, very, very large, then all your states are going to be localized. So every single state is going to live on each individual site. Now, there's going to be a transition between this metallic state and this insulating localized space. And this is what is called the critical point. And after this critical point, your wave functions are localized. And what this actually means is that when you try to inject an electron in your system, the electron is not capable of propagating. And this is essentially what gives rise to an Anderson insulator, which is another state of matter. It's a system that it doesn't have a spectral gap. So if you measure the local density of states, you see that there's no gap, but it does have a transport gap. So states exist at all the energies, but they cannot jump from one side to another side of the system forever because of this random disorder. And something very interesting is that in one-dimensional systems, you could ask yourself, what is the value of W that essentially creates this transition from extended states to localized states? And it turns out that in one-dimensional systems, an arbitrarily small amount of disorder localizes all your eigenstates. So in one dimension, no matter how weak your disorder is, then you are always an insulator. Of course, this insulating behavior appears at a certain length scale. So the localization length of your state depends on the strength of the disorder. And if the device that we have has a length that is smaller than the localization length, then it's effectively going to behave like a metal. So this is everything that I wanted to tell you today. And if I could ask you to remember something, please remember that the response to perturbations in quantum materials allows us to understand what is the nature of the underlying state, that the response to perturbations actually depends on the underlying electronic structure, and that we can predict how fluctuations are going to be in a quantum material just by understanding the underlying electronic structure. And finally, that a very specific type of perturbation, such as impurities, allows us to infer what are the properties of the underlying ground state, including potential symmetries of the superconducting order, topological invariance, and gap in quantum spin models.